Okay, hello. Can you all hear me? Hello, hello. Welcome back from lunch. We're getting back on track, more or less, and we're very excited to bring you a little inside look into what Stanford Data Science does with our early career researchers. We have a data science scholars program for PhD students who are already at Stanford, and a data science fellows program for postdoctoral scholars that are coming, well, from all over. We have some from Stanford and some from outside. We bring them together in a weekly meeting. I think John will say a little bit more about the structure of that. And so I'm going to, first and foremost, just introduce John Chambers, who in some ways doesn't need an introduction for any of you who have ever heard of the programming language R. Anyone hear of R, programming language? Anyone use the R programming language at all? Any of you heard of its predecessor, the S programming language? I know it's the last letter after R, but it's still came before R. So John is one of the inventors of S, also very involved in the R programming language. He'll have more to say about that later. But for us, he's much more than that. So for Stanford Data Science, he's a strategic advisor in every sense of the word. So some of his advice comes with, thou shalt do this, or I'm going to leave. And other advice is more like, you should really think about so-and-so. And his experience in Bell Labs, his personal character and passion for early career researchers, and his dedication to interdisciplinary science and data-intensive science has been immensely helpful for the development of Stanford Data Science, and in particular, our early career research program. So I'm very proud to introduce John Chambers.
Thank you. You did give about the first 5 minutes of my talk, but I'll give it over again. Welcome everyone, and welcome to the second half of the Stanford Data Science Conference. And I think I'm really very, very pleased with what people have done with this conference this year. Another thank out to Laura Ventura for just fantastic organizing effort. I'll echo Emmanuel on that and a number of other things as well. So basically what a lot of the program today is doing is giving everybody, this larger group, a chance to get a feeling for some of the things that Stanford Data Science does. And in the morning, you heard from one of our amazing new faculty members and various other topics that have to do with the organizations that come together to make Stanford Data Science. This afternoon, we're kind of taking a different focus. You're going to find out something in a couple of different ways about the programs that Stanford Data Science runs for early career researchers who are either graduate students currently in one of the programs at Stanford, that's the scholars, or are postdocs from various places who have come to Stanford to do postdoc work, and those are the fellows. These two groups, and I have very strong feelings for both of them, let me tell you, are just an exceptional group of early career researchers that, since I am one of the people who gets to choose them, I can just say I'm blown away by how great they are. And one of the things that is so exciting for somebody who comes from my background is that their interactions really demonstrate, as Emmanuel was saying earlier this morning, the value of interdisciplinary interactions amongst people who share a feeling for what I call data-intensive science. And these are the kinds of things that I suspect a great many of the people in this audience are involved in which the opportunities and the challenges of dealing with modern data for science are just exciting and tremendous opportunities, but at the same time they're challenging because people find themselves needing to know more than they do know and not being able to necessarily ask their co-mates in whatever discipline they're in. So the scholars and the fellows are a group that we bring together. Stanford Data Science provides them with a certain amount of financial support. And most importantly, we bring them together as a group to talk with each other, to interact with each other. They meet once a week, and the meetings involve several kinds of presentations by the participants. One set has to do with what they're called research notes. These are talks by the individuals about something to do with their research. Very importantly, I think, they are not conventional talks. Once in a while, they're a pretty much conventional talk, but they can be anything to do with the research that the person is doing. Either something that they're particularly excited about, they want to share their excitement, or on the other hand, it may be a problem they're having with their research where they'd like some advice. Or, as it has been on a couple of occasions, they may have reached a fork in the road in their research, and they'd like some comments and interactions about what should I do next? What would you do next? So these are the kinds of things which just don't take place in ordinary technical interactions, but they do, and very productively in the weekly meetings that we have. Then, in addition to those things, there are discussion periods, which for historical reasons are called data and donuts, which are, again, all over the place. They can be anything that the presenters want to talk about, usually 2 people, 3 people, sometimes 1 person. But they can be talks about technical questions. We've discussed different kinds of statistical inference, dealing with generative AI, or they can be questions of procedure, even moral questions. What kind of data should I not deal with? How should I deal with certain situations that come up in my professional life? And all of these things are just fantastically important for people to talk about. And this is a group which I think has unique opportunities for this kind of discussion, because it's a very cooperative, friendly, non-competitive group of people who share a lot of interests in a kind of science, and also, frankly, and most importantly, become good friends. Over and over again, when we ask the scholars after they've been around for a year or two, what's their most positive feeling for that? We'll get a very frequent answer is, I met some fantastic new friends. And that's really important too. So this is all very, as you can tell, into my heart, and I really appreciate it, particularly because of where I come from. So as it happens, this is almost exactly 60 years since I first arrived at Bell Labs and was exposed to the ideas which even then were circulating from John Tukey, an amazing, amazing person, and a few other people at Bell Labs who were talking about what in those days was referred to as data analysis. But I think nowadays it very clearly would be what we call data science. This was 60 years ago, and the world was very different then. I don't think any of us, maybe not even John Tukey, could have anticipated the magnitude of the changes that have taken place since then. But I think many of the ideas that he was pushing and that other people were pushing have still stood the ground. And in particular, I always treasure one of John Tukey's emphatic statements, which was that data analysis, justification for data analysis is science. And I think that's an important thing that I would bring to data science now. Data science is a field with a lot of techniques and exciting things going on, like the things that Emmanuel talked about. But fundamentally, I think the data science that I'm interested in anyway is in the service of science. And that is what we try to do, is to build the science for now and for the future. And as Emmanuel again was saying, that's one of the real goals of Stanford Data Science, is to provide for the future. So what does that mean? When you think about the future and the future of science, I think it's an amazing, frightening prospect. I think both the opportunities and the challenges of the next decade or so for science are just huge. In the most basic sense, I think there are so many fields of science where the new data-intensive world is just exposing possibilities for fundamental knowledge that were never there before. Before this morning's talk, I had two particular examples in mind, and one is the nature of the universe. I think if you look at what astronomy and cosmology are involved in now, there's simply a revolution in the size and in the nature of a lot of the data. We're able to ask questions about the universe we couldn't ask a decade or 2 decades ago. And similarly, the nature of life itself. How did life begin? What is the real mechanism of life? Once again, new data, new technology, and new ideas are just opening up fundamental questions in this area. But Laura's talk this morning exposed one more, the nature of the human brain and thought. And once again, as she so eloquently expressed to us, there are new sources of data just radically different from what was available in the past. So there's these opportunities. And in addition to the opportunities in fields of science that are already established, there are many fields where for the first time in any serious way, quantitative thinking is becoming part of the process. As one person who's in the audience today could tell us in great detail, one field where that applies is the law. Other fields like history, even classical languages. Once again, there are quantitative possibilities within these fields which were not recognized before. And so one of the things that we see in our multidisciplinary group is that we're able to bring people in who are involved in science, involved in data-intensive science, in fields where they will not indeed be the majority. They will perhaps feel kind of lonely. And for them too, this interaction, this community of supportive and friendly people I think, has proven to be a very important asset for them to have. So that's what we're doing here. I think it's important. I think it's particularly important for the future of science, and science is going to have to deal with some really important practical problems as well, and that brings us to several topics. But one of them is the one we're going to spend the rest of this session doing. So what's going to happen this afternoon is two things. In the rest of this session, Emily, Thomas, and Iván will take you through a replay of a very exciting and interesting, to me certainly, discussion session that took place with the scholars and fellows recently this year. And that is the nature of climate science, of science as applied to modeling the climate, predicting the climate. Now, this is a topic, of course, which is very much on everyone's radar, and we all, I suspect everyone in this room has read through or looked at the various reports on that. And some of us, including myself, have gone beyond that and tried to look at some of the original source material. But I've felt until their presentation that I was missing the big picture. How does this all fit into the idea of data-intensive science, which is clearly necessary for modeling the climate? And I found that their presentation to us was the clearest and most helpful I'd ever heard on this topic. So I twisted their arm a little bit and convinced them that they could give you necessarily a reduced size, reduced length presentation that will give you a feeling for this discussion. And by extrapolation, I think it will give you a feeling for the kinds of discussions that go on in this marvelous group. then in the next session following this one, you will get a chance to participate in a discussion along the same style as we have for this group. And I hope you'll find that exciting. But at this point, I am going to shut up and let Emily, Thomas, and Iván tell you about climate science.
All right, so yeah, just echoing what John said, we're really fortunate in the Scholars and Fellows program to meet together once a week and talk about topics in data science. And fairly early on, Iván, Thomas, and I figured out that we had a shared interest, research interest in climate, and we sort of had these intersecting research interests, which sort of coalesce around this idea of climate modeling and understanding future climate change using data science. So the sort of inspiration for our session was how do we go from our fundamental understanding of physics to projections of future climate change, and where does data science come into that? So I'm going to start by talking actually about the data generation. So where is the data coming from that we make these projections with? So on the right here, on the left is the Navier-Stokes equation. So these are our fundamental equations. And then on the right is a figure from the IPCC report looking at future changes in heat and extreme precipitation under different warming levels. So we use climate models to understand our climate system, but we need to make a lot of decisions about how we model the climate system. So we have our equations, but we need to then decide what are we going to do with our planet Earth. Earth is a sphere, so we need to figure out how we're going to cut that up into its little box sizes, into little boxes. So the top left shows a cube sphere where we put little cube spaces on it and we divide it into rectangles and we pass information between our rectangles. The top right is showing spectral methods, so we might just go, actually I don't care about doing this in space, we're going to do this in spectral mode. And then the bottom middle one is a kind of a fun grid that people play with, which is hexagons, so you can just cover the Earth in hexagons instead, and then so advect fluid between all the different all these different grid boxes. And so that's just one choice you need to make. The other thing is sort of things like vertical coordinates. So are you going to be in pressure coordinates or many myriad choices? What's your resolution going to be? So you need to make choices about how big your grid boxes are going to be, because it becomes really computationally expensive. The smaller the box are, the smaller the time step. You have to make those sorts of decisions. But then this becomes another problem, is that any process that is smaller than your grid box size has to be parameterized. So this is the idea that we need to, we can't fully realize the process within this grid box, and so we need to come up with some sort of relationship that we can solve within this grid box to represent that process. So this figure here is showing, just in one grid box, what are the sort of things we're going to have to parameterize. So the radiation scheme, so the sunlight coming in, how does that interact with clouds, with moisture? How do clouds even form? So we have tons of different cloud processes. Here I've just outlined one of the types of cloud formation, and then this is the scheme for generating those clouds. We also have to think about our topography. So are we over mountains? Are we over the ocean? And things like that. So numerical modeling becomes really big really quickly, and we're having to make all these different decisions about how we're going to generate our data. Okay, so we're in 2024 now. Climate modeling started in about the 1960s with these single column atmospheric models, and then they were soon coupled to an ocean, and then we expanded them over the globe. And then as we've gone along, we've added components. We went from having our atmosphere and ocean to having sea ice at the poles, and then including things like biogeochemistry, aerosols, raising the top of our model so we can do higher up processes in the atmosphere, adding ice sheets, that sort of thing. And it's not just one model that I'm talking about here. I talked about all these different assumptions, all these different decisions we make, and the different modeling centers around the world sort of represent the different ways we can approach climate models. So on the right here is showing around the world places that have contributed models to the IPCC, which we will talk about in a sec. all of these different institutions make different assumptions when they build their climate models. And so they're generating these experiments with all of this data, which have all of these different assumptions that we can learn about our Earth system. And so these are just 3 different climate models I'm showing here. Their different components and how they're all coupled together. And so these days, a climate model will have at least an atmosphere and ocean component, and then maybe also sea ice, land surface, land ocean, biogeochemistry, and rivers and ice sheets. Okay, so we take all of our climate models and we want to understand what are the different things we can learn about our system with climate models. So we do these things called model intercomparison projects. And so we can learn about our system's response to forcing. So how do these different models behave if we chuck a ton of CO2 in there? We can look at the biases. So what are our different models getting wrong and what can we learn about our system? And then also what can we learn about the sort of internal variability, which is how our Earth system behaves even without forcing. And so I'm going to pass over to Thomas now, who's going to discuss more about MIPS.
Yeah, so thanks, Emily. So what I actually work on is I build radar instruments that are used to study Earth's ice sheets. And so I come at this from a bit of a different angle, but I think it's really important to understand where the data that you create or that you're trying to create will flow into. And so that was one of the things that was great about working with Emily and Iván on this, is sort of understanding this bigger picture of how these pieces go together. But that's also your context for why, out of all of these things, I chose to focus on ISMIP, which is the Ice Sheet Model Intercomparison Project. So Earth's ice sheets are on top of Antarctica and Greenland. And so that was the sort of the piece of this that I'm most familiar with. But the general principles of how this works applies across all of these model intercomparison projects, more or less. So what happens when you have one of these model intercomparison projects is basically a whole bunch of scientists get together and they talk about sort of what are all the variables they want to consider, and they kind of come up with a standardized set of experiments. And it's standardized not so much in the sense that they're making every group make the same. Don't worry, you don't need to interpret all of this. It's not standardized in the sense that everyone's running the same experiment. It's standardized in the sense that they're basically coming up with a common language for all the different decisions that they're going to make. So Emily talked about some of the numerical decisions you have to make about how you discretize. There's also decisions about what physics you're going to impose, like what kinds of physics you're going to solve for. What are the boundaries going to look like? How are you going to couple different pieces of the system together? What input data sources are you going to use, and how are you going to interpolate those things? There's all of these different choices before you even get to something like, how much carbon did we pump into the atmosphere, that have to be made that go into these models. So with some common language and some common framework created, a whole bunch of different groups go off, largely on their own, and make these decisions. So these are all of the groups that submitted Antarctic model runs for ISMIP 6 for one of the sets of experiments. And you can see they've made different choices that are kind of summarized in this table here, ranging from numerics, physics, boundary conditions, data sources, et cetera. And in some cases, they may be using the same model, which is what I've highlighted in the little colored blocks on the side of the screen here. But even using the same underlying model, they're making so many different assumptions that these are really sort of independent experiments that are being run. So that's great. We can look at the results of this, and we can get some sense of what modelers expect the future of Antarctica or Greenland to look like. But how do we condense this into something that we can sort of interpret rather than looking at the individual results of every one of these? And this is where another piece of the data-intensive science here comes in, where basically what happens is other groups try to make emulators of all the model outputs. So in this case, this relies on Gaussian process emulation. There's a couple different tools that are used here. But basically the idea is to create some sort of interpolator and uncertainty estimator between all of these different models. So you take all these model runs, and then you try to add another layer on top of that, where you model as a function of various input parameters and various design choices. What do you expect that model to say? In this case, for how much mass will be lost from the Greenland ice sheet by the year 2100. So you make some decisions about sort of what are the inputs you're trying to control for. The remainder of the differences that in what the groups have chosen to do becomes sort of your variance, your uncertainty in your output. And this allows us, this creates a tool that we can use to do two things. One, we can use this to interpolate between model results. So if we're interested in a particular set of parameters, but no one group modeled exactly that, we can still sort of interpolate based on the what other groups submitted and understand what we would likely have gotten. And second, even when different groups modeled the exact same set of parameters, maybe they got different results because of some of those design decisions they made. So this allows us a way to sort of estimate uncertainty out of that and understand how certain or uncertain our predictions are, which just gives us some idea of how well we're doing at estimating the sort of future evolution of these ice sheets. So all that eventually goes into many things, but among the most important, it goes into IPCC reports, which is the Intergovernmental Panel on Climate Change, and they create these summary figures that are built out of the emulators that show policymakers sort of what is the range of possibilities to expect under a certain set of emissions scenarios. So I'm going to turn it over to Iván now to talk about sort of what this means for humans and the impacts of this are.
Cool. So as social scientists, we want to know what's going to happen with us. And certainly, as Emily and Thomas have introduced already, we use the IPCC scenarios. And what these scenarios tell us is like we have like many futures that can happen. One of those, we're all dead. This is like our SSP tree 7.0, which is like a forcing or like how much CO2 we have in the atmosphere. But also we have like a nice scenario in which, things can be bad, but we're there, we're surviving. But at the same time, if we're able to curb all sorts of emissions before 2030, we will be like, okay. And what the models allow us to do is to think on how these possible scenarios and how our lives look on those. So to do this, my group and other groups, and also the IPCC, use historical response functions based from causal estimates, the ones that Ambarish talk and Basilis and others, using causal inference to understand the relationships between temperature and things like GDP or mortality, and we project those estimates into the future. We also care about uncertainty, so we have different processes to account by that. And for instance, one of the most famous examples is in this scenario, we're kind of there. This is what will happen to our GDP. But this is not the complete picture. We know that even in this scenario where we're kind of so-so, we have some winners, and we also have some losers. So if you're in Norway, it's going to be okay. If you're in Canada, probably okay. But if you're in Latin America, Africa, or the Middle East, things are going to be very different. We also can answer questions using these models. These are different. Each point is one of the models that Emily showed, in which we have different realizations in mortality, and we can actually devise how much mortality is going to cost us in the future, which is around 40-50% of the GDP in the present. We can also see how wildfire emissions are going to behave. This is the work from Minghao Xu from my lab, in which he projects the amount of emissions coming from dry matter from wildfires in different in the northern hemisphere. But more importantly, and this is a beautiful paper from my friend Chris Callahan, we can also see how air density, which is correlated with temperature, can also make baseball more fun, because we will have more home runs as air density decreases. So this is basically what we're seeing here. Under these scenarios, we can see that if you focus your attention here, Wrigley Field in Chicago will have a larger amount of home runs in the future, which can only mean one thing, is that probably we'll have a World Series champions at the end of the century. So one of the things I wanted to showcase here is we can connect the people in the physics world, like Emily and Thomas, and people in the social sciences that do this kind of sorcery with the stats and causal inference to basically take those Navier-Stokes equations and answering very cool questions about what's going to happen with the future GDP, but also what's going to happen with baseball.
This is a very fast run through what was much more detailed and, of course, much more sophisticated presentation to the group. But you can sort of see why it was a lot of fun. And we do have some time for questions. So if people would like to ask any questions to the group. I think, do we have microphones there?
Hello. Oh, I was wondering how you three met and started collaborating, or whether you collaborate in your daily work.
Yeah, so we connected through the data science program. Just like met at one of we have our weekly meetings. I think it was after like the first one. We all say did a brief intro on what we were interested in, and yeah, I don't think we have any formal collaboration right now, but yeah.
I guess I was going to offer a couple things. So I don't know if you know Professor Feigenbaum. He was one of the fathers, they say, of artificial intelligence, and he worked on that discretization problem back in around 1980. So what you're trying to do is something that Stanford's been trying to work on for a long time. And so I would maybe just go look up that reference paper. It was a PhD student. The second thing is, so I've worked in computational fluid dynamics for 50 years, 45 years. There's a tremendous amount of work on what you're trying to do in terms of sorting out the uncertainty between algorithms and equation sets in the aerospace computational fluid dynamics area. So I just offered that to you.
Thanks.
What are the major systematic differences you see between the climate models? Like, what are the major systematic differences?
Yeah, so I think so. In terms of what I outlined, it is the fundamental underlying assumptions about how we break up our planet, but then there also is different ways of doing these parameterization schemes, and I think when it becomes really interesting is how it manifests in the data that they output, and so you do get these differences in things like temperature projections, and then that's when the sort of pulling together all those different sources and projecting uncertainty is, I think, what becomes really fun and interesting.
Yeah, I can add to that slightly because I think it looks related but slightly different maybe from like the ice sheet side. I will not speak to the atmospheric climate models, but on the ice sheet side, a lot of it really comes from like boundary conditions and choices of how you're going to deal with those boundary conditions, especially the interactions between ice and ocean and ice and atmosphere. And those are places where we understand the physics not as well as we understand the physics when you're just in the ocean, just in the atmosphere, or just in the ice. And so decisions that are made there about how to parameterize it, how to discretize it, those kinds of things become a really big deal.
Hi, can you talk a little bit more about maybe the use cases of these deterministic models as opposed to stochastic modeling in this day and age, if there are any?
Yeah, okay. Like I said at the beginning of this, ice sheet models are not really my field. I make instruments that go into ice sheet models. That said, there's a ton of interest in stochastic ice sheet models. There is now one of them as of like 2 months ago. So that gives you an idea of kind of how new this is. As one of the previous questions mentioned, like there's a lot of techniques that are still sort of being incorporated into this that have been developed in other fields that are being ported over. It really depends on the kind of uncertainty that you're trying to get at, right? So stochastic models are really fantastic for understanding, like if you have like uncertainty in some of your input fields, like how does that impact it? If you're really trying to figure out like what are the right physical parameterizations, like to what level of physics do we need to resolve things, then it's very useful to work across like semi-independent modeling groups that can make those decisions and justify them and see how those results do or don't compare. So I think to some extent, it's just the continued evolution, and we need more work in the stochastic modeling space. It's just been sort of computationally challenging. but we're getting there. I think it's an exciting frontier that we just haven't fully unlocked yet.
Really enjoyed them. So you're working with spatio-temporal data, and I can think of another domain that makes recordings over space and time, neuroscience. And I'm wondering if you could speak a little bit more about those models that use space and time, and to what extent you think they might be kind of generally applicable to other domains.
Yeah, I mean, there's 1,000 answers. It's a great question, and there's 1,000 answers to it. There's probably a couple people in the room who could get better answers than I can. I think, as far as the like data science side of this, there's more and more work on data-driven methods to do things like estimate parameters of sort of uncertain coefficients in physical equations. And those, I think, are places where there's some interesting overlap, where you have to consider the sort of spatial patterns of some of these things. And like, for example, if you're to give like one simple example, if you've got a whole bunch of data points that are spread across some domain, you can't just like randomly go split those into like training and test, because there's a strong spatial correlation. And so you can get things wrong if you fail to account for that. At the same time, you can learn a lot from the spatial correlations and from the covariance between points, and sometimes that can be used as a really effective technique to interpolate fields using the spatial context between them. So I don't know if that answers your question at all, but you want to?
Is it on? Yes. Is it on?
I think so.
It's on. Sorry. Yeah, I think everything Thomas said, and then also that I think we're starting to get better at that now. I think we used a lot of dimension reduction early on, and I think we're really starting to figure out maybe some better ways around that.
One more
Hi.
question?
Yeah, sorry, one more. Thanks for the talk. Do you guys envision some sort of like future model, like grander model that like combines different aspects? And what do you think is missing for that? Like, do you need someone to like, is there a lot of work that needs to be done to like join the two models together? Does someone have to do that separately, or is there like an avenue for that?
I mean, yeah, it's a great question. There's, I think, tons of work of how to like link different components together. I think there's also questions about, okay, if we're going into the future, do we want to think about going higher resolution so we don't have to do as much of the parameterization that we're doing? What is the role of AI? We didn't even talk about AI there, but AI, where can we best use that within the existing models we have, or do we want to like just start building models that are totally AI? That's my sort of 2 cents on that. I don't know.
Yeah.
Okay.
There's certainly lots of people working on more integrated versions, but there's also safety and beauty in diversity of models that do not have common origins.
So I think we've been whacked. Thanks for the questions, and I hope you got a feeling, even in this very condensed form that we've had to use, but how exciting this kind of discussion is when we get all these different viewpoints together. So thank you for joining, and go on to the next.